Hello everyone. So in the last class, what we looked at in module 2 was a discussion of the attributes of turbulence. And the attributes included irregularity, diffusivity, a very important attribute which we'll discuss in detail in today's class, large Reynolds numbers, 3D vorticity fluctuations, and dissipation. Again, a very important attribute. Additionally, we also looked at the continuum assumption. So the continuum assumption is valid here. And the fact that turbulent flows are flows. It is not a fluid property. It is a flow property. Further, we went on to look at methods of analysis. Dimension analysis was one. We looked at asymptotic invariance and later local invariance, where we could use the right quantities to scale things like energy spectra to find similarities between different kinds of flows. And this plot, we discussed this in detail as well. So today, what we are going to do is we are going to start by looking at the origin of turbulence. So how does turbulence start? Essentially, that's what we are trying to answer by looking at the origin of turbulence. So in flows which are originally laminar, turbulence arises from certain instabilities. These instabilities start at certain points in space and certain points in time, and then they propagate. What determines whether they propagate or not? For example, in a pipe flow, flow becomes transitions from laminar to turbulent at a Reynolds number of approximately 2100. So this Reynolds number is approximate. It is dependent on, say, for example, the smoothness of the surface of the pipe. The roughness causes the transition to happen sooner. So for a smooth pipe, the Reynolds number is around 2100. Where the flow transitions from laminar to turbulent. So that is, we call it the critical Reynolds number, right? And if you have a boundary layer or flow over a flat plate, the boundary layer at say zero pressure gradient, that becomes unstable at a Reynolds number of approximately 600. So that is what is listed here, where you have the Reynolds number of U delta star over nu approximately equal to 600. Delta star being the displacement thickness. So that is the characteristic length scale. Here, the Reynolds number for pipe flow would naturally be U d over nu, where d is the diameter of the pipe. So this would be a characteristic length scale. Here, when you're talking about free shear flows, such as flow in a mixing layer, they become unstable at very low Reynolds numbers because of certain inviscid instability mechanism. Here, the inviscid instability mechanism is not what operates in a boundary layer or a pipe flow. Okay, so because of that, the instabilities start to propagate at a lower Reynolds number. In pipe flow and boundary layer flow, you have a solid surface. So you have a velocity gradient because of that. Whereas in free shear flows, there's no solid surface bounding the flow. In that sense, it is an inviscid instability that creates that is the origin of turbulence there. Also note that turbulence cannot maintain itself. It needs to have a constant supply of energy, and we looked at this in the previous class as well. So some common sources of energy would be shear and buoyancy. You need shear and buoyancy for the turbulence to keep propagating. So this figure illustrates, say, flow over a flat plate. You have boundary layer over a flat plate. And initially, at the leading edge, where the flow is coming onto the plate, okay? Here, as the flow is coming onto the plate, you have flow that is laminar. So laminar flow will have features such as smooth flow, regular flow, very predictable flow in layers, and a profile would look something like this. This is marked by low mixing, as in the mixing is actually at a very low rate. So that is what we are representing by du dy being a very small number, being much less than 1. So that is the low mixing scenario, laminar flow. Now as the flow keeps moving from left to right, you start to have instabilities in this region, the transition region. Those instabilities will occur at certain points in space. Sometimes they occur over a period of time, they go away, they come back again, and so on. Those instabilities, depending on the Reynolds number of the flow, they tend to propagate. And eventually the flow transitions to turbulent flow. And the profile in a turbulent flow looks like this. This is marked, the turbulent flow is marked by very high mixing. The velocity gradients are high. So that is what I mean by du dy being much greater than 1. So that is how it starts, right? It starts from laminar flow, then the instabilities begin to happen, and those instabilities propagate depending on the Reynolds number, and eventually the flow transitions to turbulent flow. So this is sort of a figure illustrating that phenomena. Now, if turbulence arrives in an environment where there is no shear or buoyancy or any other maintenance mechanism, it will decay. And we discussed this even in the previous class. You need a continuous supply of energy. And if there is no shear or buoyancy, there is no way for the turbulence to keep happening, to keep propagating. So eventually the turbulence will just decay. The Reynolds number will decrease as a result of it because the turbulence decays, and the flow will tend to become laminar again. An example would be, say, turbulence produced by a grid in a uniform flow in a wind tunnel. Okay, this is a grid turbulence experiment. This is a typical grid turbulence experiment that is run in a lab. You have an actual steel mesh. You have an actual metal mesh here through which flow is going through at high Reynolds numbers. And as the flow is going through, the flow becomes turbulent here, but there is no mechanism that keeps up the shear or the buoyancy as it is going through. So eventually the turbulence is going to decay. So what we have is a decaying turbulence here. The turbulence is decaying as I'm going from front to back. I have decaying turbulence here, and the flow eventually just becomes laminar towards the end. This is what Taylor used as his hypothesis to convert the spatial data into temporal data. This was the Taylor's hypothesis that I have discussed in module 1. It is this kind of data where the turbulence decays over in space, and this could be converted into temporal data and used for several correlations, both for comparing computational models, for correlating with other experiments, and so on. So this is an example where you have an environment where there is no maintenance mechanism, either through shear or buoyancy, and the turbulence decays. So I talked about an example where the turbulence decays. Another way to make a turbulent flow laminar, okay, in other words, the laminarization of a turbulent flow, is to provide a mechanism that consumes the turbulent kinetic energy, that takes up the turbulent kinetic energy. You can do this through an imposed magnetic field, for example, at very low magnetic Reynolds numbers. Okay, that's one way to do it. Impose a magnetic field, and that will sort of stretch the flow and re-laminarize the flow. Another way to do it is through stratification, through a stable density stratification. So stratification means change in density. You have a density gradient. That's what stratification is. In atmospheric flows, it does, you have a stratification that exists in atmospheric flows that can that can relaminarize a flow, that can reduce the turbulence by stretching the flow in one direction. So mathematically, the details of transition from laminar to turbulent flow is actually not well understood. So several experiments have shown that transition is initiated typically by some kind of an instability mechanism, which in most cases are in 2D. Okay, but this instability eventually generates or introduces, I should say, secondary motions which are actually 3D, because turbulence is 3D. But the instabilities in some cases could be just 2D. So this sequence where you have instabilities that are created and which creates secondary motions, 3D secondary motions, these are localized disturbances. Also, we call them turbulence spots. And they arise in random positions at random times. These spots, they grow rapidly, merge with each other, become large, and eventually lead to the formation or the development of a turbulent flow. So that is the origin of turbulence. Starts from laminar flow, then there are instability mechanisms. For example, in a pipe flow or in a boundary layer flow, as in flow over a flat plate, there are instability mechanisms due to the velocity gradient. In free shear flows, the instability mechanism is inviscid by nature. These eventually merge with other disturbances, other instabilities. They occur at random spaces at random times. They merge with other spots, other instabilities, become larger and propagate further. So that is how, and eventually develop into a turbulent flow. So that is how turbulence flow originates. Our next topic is the diffusivity of turbulence. So this is one of the main attributes of turbulence, like I was discussing earlier. And I want to spend some time discussing this in detail, as this is one of the main attributes of turbulence. We will discuss this particular attribute through a case study. So diffusivity is sort of the outstanding characteristic of turbulent flow, and it represents its ability to transport and mix momentum, kinetic energy, or even scalars such as moisture or any kind of species, even heat. So it is its ability to transport or mix momentum, kinetic energy, and other scalars, right? Contaminants such as heat, particles, or moisture. Here, in the case of turbulent flow, the rate of transfer and mixing are several orders of magnitude as what you would have in a laminar flow. In a laminar flow, what is the diffusivity? It is the molecular diffusion. And we discussed this as well briefly. Where in turbulent flow, it is this diffusivity which is a flow property, and the rate at which diffusion happens in a turbulent flow is much faster compared to what would happen in a laminar flow due to molecular diffusion. An example would be, consider some kind of a combustion chamber, say an incinerator. Here you have the heat transfer and combustion rates in this turbulent combustion are orders of magnitude larger than corresponding rates, for example, where laminar combustion occurs, and I mentioned this example like in a laminar flame, like in a candle flame. So we are talking about fire in a chamber such as an incinerator, and the rate of combustion is much larger, okay, as in orders of magnitude larger than what you would see in a candle flame. So the case study we are going to look at in order to discuss this problem in more detail, in order to discuss this attribute in more detail, is, say, a problem with an imposed length scale, which is, let's consider a room, the room that you're in right now. Okay, so if you have a room where there is some radiator or some heating element that is installed. So that is generating heat within the room. The room, let's say, has a length scale L. So this L is some kind of a cube root of the volume of the room. Let's say the room does not have the same length, breadth, and height. All are different. You can a typical characteristic length scale could be the cube root of the volume of the room. Okay, so for example, L would be approximately equal to the cube root of the volume of the room. That's a characteristic length scale for the room. Now consider in this room first, the first case is where there is no air motion in the room. There is a heater that is generating heat. Now the heat is distributed into the room. If there is no airflow, the heat is distributed in the room purely through molecular diffusion. And the process is governed by the equation shown here. This is the heat transport equation. It's you have the unsteady term on the left and you have the diffusion term on the right. Remember, advection does not exist because there is no air motion. So you have del theta del t is equal to gamma times del squared theta del xi del xi. What is gamma? Gamma would be the thermal diffusivity. So it's a property of the fluid, in this particular case air. Del theta del t is gamma del squared theta del xi del xi. Now what I want to do is I want to dimensionally analyze this equation. I don't want to solve the equation. I don't want a solution for this equation. But I want to dimensionally analyze this equation so that I can understand the consequences of turbulent flow in the context of this particular problem. That is what I'm going to do. So I'll dimensionally analyze this equation by representing each quantity in this equation as scales. So I can think of, on the left hand side, del theta, say it could be interpreted as delta theta. So that is this equation number 2 that I'm showing here. Delta theta, which is dimensionally of the same order as del theta. And then delta theta over Tm represents an order of magnitude analysis of the left hand side of equation number 1. Delta theta over Tm. I'll tell you what Tm is. It's a time scale that is involved in this equation. Delta theta over Tm is gamma, which is again the thermal diffusivity. I keep that as such, multiplied by delta theta over L squared, because I again have del squared theta here. So on the right hand side too, I will have delta theta, divided by del xi. My order of magnitude analysis allows me to write this as L squared, because I'm doing an order of magnitude analysis. So each term I'm writing it as how I'm writing it in terms of the order of magnitude. So del theta is of the order of magnitude of, say, delta theta, a characteristic temperature difference. Del t is of the order of Tm, which is a time scale. I have a subscript m to represent the fact that it is due to molecular diffusion alone, as there is no airflow. On the right hand side, I have gamma and I have delta theta over L squared. I cannot use an equal to sign here because I'm doing an order of magnitude analysis, so this is of the same order. Now from this equation, the delta theta and delta theta on both sides get cancelled, and what I have is Tm is approximately equal to L squared over gamma. This is what I have. So I have a representation for the time scale. Again, Tm represents the time scale associated with this problem, where there is no airflow and only molecular diffusion, hence the subscript m, which is L squared over gamma. So now let's try to come up with some numbers. We know that we have air in the room. There is no airflow, but it is air in the room. Standard temperature and pressure, atmospheric pressure, standard temperature approximately 300 Kelvin, right, 27 degrees C. And if I consider L to be 5 meters, a typical length scale for a reasonably sized room, Tm becomes of the order of 10 to the 6 seconds. 10 to the 6 seconds translates to about 100 hours. So that's the time scale associated with the transport of heat, the distribution of heat within this room. So you can now guess that this kind of heat transport, if it takes 100 hours to distribute the heat in the room, you can recognize the fact that it is rather ineffective. So the conclusion is molecular diffusion is rather an ineffective tool or mechanism in transporting the heat within a room of this size. It's about more than 100 hours. Now, let's consider a scenario where there is some airflow, okay? Even fairly weak motions, such as, say, those generated due to small density differences, buoyancy. And there is buoyancy in the room. So even the buoyancy within a room that is approximately of height 5 meters can generate very small density differences. And we'll see how even those small density differences will lead to a little amount of airflow, which can actually disperse the heat much quicker. Let's see that. So let's say I have airflow, okay, and let's say the motion is again characterized by the length scale L. You will have motions that are present that are of scales much smaller than L, but you can still use L as a characteristic length scale. L is approximately the cube root of the volume of the room. Okay. Now, when you have airflow, okay, and this is turbulent airflow, when you have airflow in here, since airflow is associated with a velocity, you will also need a velocity scale. So a characteristic velocity. So typically this can be thought of as an RMS of the velocity fluctuations, an RMS amplitude of the velocity fluctuations. Okay? So this is different from the previous scenario where there is no airflow. Now you have turbulent airflow, so you have to think of the velocity scale, and the velocity scale can be assumed to be the RMS amplitude of the velocity fluctuations. So now your characteristic time scale is Tt is equal to L over U. Well, L is the characteristic length scale. Again, the size of the room, order of magnitude of the size of the room, divided by U, which is the RMS amplitude of the velocity fluctuations. So as you can see, you can only determine the characteristic time scale in this particular case if you know the velocity within the room. As opposed to, in the previous case, the time scale could be determined purely by knowing what is the length, which can be measured, and what the air fluid is in the room, which is air. So L squared over gamma. So in turbulent flow, so this is already determining the time scale is already very different, right? So let's try to come up with some numbers. Since we don't know what the velocity is, let's try to put some numbers in play and see what kind of magnitude we get. So let's say the radiation heats the air in its vicinity by about delta theta. Okay, so let's say there is a change in temperature by delta theta because of the heat generated from the radiator, from the heating element. There's a change in temperature by delta theta. So this will cause a density difference, and this will and hence it will consequently cause a buoyant acceleration of, say, g delta theta over theta. Now theta is approximately, theta is approximately 300 Kelvin, right, standard temperature, and delta theta over theta and multiplied by g gives you 0.3 meter per second squared. So that, you get that by taking 10 times, say, approximately 10 delta theta, you assume there's a 10-degree temperature difference, divided by 300. So that is approximately 0.3 meter per second squared. That's how I come up with that number. If the radiator has a height of, say, 0.1 meter, reasonable assumption, the kinetic energy of the air above the radiator is, say, gh delta theta over theta. So this is the energy per unit mass, isn't it? Like potential energy. I take g delta theta over theta, which is the acceleration, multiplied by h. That gives me the kinetic energy per unit mass. So that is 0.03 meter squared per second squared, assuming h is about 0.1 meter. Again, we are doing order of magnitude, not exact numbers, but these are reasonable assumptions. So this kinetic energy per unit mass corresponds to a velocity of 17 centimeter per second, right? Kinetic energy per unit mass would be half v squared, and in order to find out the velocity, you can just multiply by 2 and take a square root. So then you get it to be 17 centimeter per second squared. So based on that, 1/3 of that velocity, okay, can be considered as a characteristic velocity. So assuming the fluctuations are 30% of the actual velocity, which is again a reasonable assumption, 5 centimeter per second seems to be a reasonable assumption for the RMS amplitude. So with u is equal to 5 centimeter per second and L is equal to 5 meters, the characteristic length of the room, the turbulent time scale can now be determined. It becomes 100 seconds or 2 minutes, approximately 2 minutes. So you see the difference. You had with molecular diffusion about 100 hours. 100 hours, right? 100 hours. And then now you have 2 minutes. 100 hours versus 2 minutes. That's the difference between a laminar flow and turbulent flow. This is what diffusivity in turbulence does. So what happens is the turbulence generates eddies as small as about 1 centimeter, and this estimate we obtained from dissipation equations. I have not gone into that here. We will discuss how to come up with those assumptions, those numbers much later in the class. But actually eddies as small as 1 centimeter are generated from this kind of turbulent flow. So the temperature gradients associated with these small eddies are then smeared out by molecular diffusion. So I'm talking about dissipation here. And in a time which is approximately of the order of L squared over gamma. So here L is approximately 1 centimeter. These are the smallest eddies. Huh? The smallest eddies are dissipated by molecular diffusion. So if you just calculate L squared over gamma, gamma again being the value at standard temperature and pressure, which is the same thing we used for the molecular diffusion case in the room, these time scales are only a few seconds. So what are we trying to say here? The time scale for heat to be distributed in a turbulent flow is of the order of 2 minutes, much faster than what you would have in a laminar flow where you only have molecular diffusion. And the time scale at which the smallest eddies, which are of the order of 1 centimeter, dissipates due to molecular diffusion is a few seconds. So this is how different turbulent flow is compared to laminar flow. We illustrated that through a case study represented by a room and heat transport in a room. And we looked at two cases, one where there was no airflow, so heat is transported only through molecular diffusion, and one where there is a turbulent airflow. And you saw the difference. Thank you.